Okay, so we've told you how to use Newton's second law to solve inclined plane problems and to solve Atwood's machine problems. Now I want to tell you about how to use Newton's second law to solve circular motion problems. Okay, the key thing to remember with circular motion problems is for uniform circular motion, the acceleration is v squared over r. The acceleration's magnitude is gonna be the speed of the object moving in circular motion squared divided by the radius of the circle, and it's always toward the center. The acceleration is always toward the center. So let's see how this works. What I like to do, I think the trick to solving circular motion problems easily is to have it be one running equation all the time. Don't try and have a bunch of different equations going at once. Just have it be one running equation. So let me show you what I mean by that. Let's say that you're on the top of a Ferris wheel. You're coming around the top of a Ferris wheel. So here you are on the seat. That's the seat. And here you are sitting down on that seat. And you're going with a speed v, going this way, let's say. You're coming around. And they want to know what the force, maybe the question is, what will be the normal force, or the force of the seat on you? So what will be the force of the seat on you? So draw your force diagram. Your force diagram is, you got mg down, and you have a normal force. The seat's pushing up on you. That might change depending on what type of ride we're talking about or what's the situation. So the force diagram is not always the same for these problems. That you got to get that force diagram right. I mean, take some time and get it right, because if you get it wrong, you're not going to get the problem correct. Okay, notice I made mg bigger than Fn. That's because if you're here, if you're going in a circle, see the circle you're going in? You're accelerating toward the center. And so you need this to be the bigger force so that your net force is toward the center. Also notice that I don't have centripetal force. Don't throw a third force in here, centripetal force. The centripetal force is just a fancy way of saying the net force. So don't go and put a F sub C in there thinking that it belongs in there. It never is going to be in your force diagrams. Okay, so this is how easy it is. You say A equals F net over M. But I kind of know the A. The A is V squared over R. They would have to tell me the radius of the circle I'm going in. Now, that's equal to the net force. And what would you say the net force is? I would say, since this one is winning, it's accelerating downward, it's mg minus the normal force. All over, that's A equals F net all over M. So if they want me to solve for the normal force, then maybe bring the M on the other side, and that will equal mg minus Fn. And then I can maybe take the Fn on this side and this term on that side. So apparently Fn, just for this situation, is going to be mg minus mv squared over r. A second part to this problem might ask, what's the fastest speed that you can go before you'll start to leave your seat? Or at what speed will you start to leave your seat? Well, when you start to leave your seat, that means the normal force is zero. Like the seat can't push on you anymore if you're starting to leave your seat. So if you want to solve for the maximum speed you can go and not leave the seat, then just set that equal to zero, and that will solve for v. it kind of makes sense that when you're up there, you're going to feel very light-headed. When you go over this hill, it's kind of like being on the Viper at the top of a hill. As you crest the hill, you feel very light. And the reason for that is because your normal force is much smaller than normal. In fact, your normal force is mg, what you normally feel, minus this term. Okay, now here's the point. This is a very important point. Don't try and memorize these, because this changes all the time. And you know, the beauty of physics is that this equation and a little thinking, just a bunch of, you know, some basic equations and a little thinking and math get you to these. So that's one of the cool parts of physics. Don't try and just memorize your way through physics. First of all, you'll hate physics. And second of all, it's going to be a lot harder. Okay, let's try a different one. Let's say you want to find the speed of a satellite in orbit. How fast does a satellite have to be in order to orbit the Earth at a radius of 2r, let's say? So here's the Earth. Here's the radius of the Earth. You're out here a distance, a whole nother RE away from here. And the question is if you want to go in a circular orbit, what speed do you have to go at so that you don't come plummeting down to the Earth? Again, if you draw the force diagram of the satellite, the force diagram looks like this. There's just one force on it. It's the force of gravity. There aren't any other forces on this. There's a force on the Earth. There are of the satellite pulling on the Earth, but we're just looking at the force on the satellite. So A of the satellite is equal to the net force on the satellite all over the mass of the satellite. So A of the satellite is v squared over r. That's the speed of the satellite squared divided by r. Now I'm going to make that 2re, because isn't the radius of this circle 2re? That's 2re, so I'm going to say that's 2re. That's equal to the net force. Now the net force is just this force, remember this guy? That'd be the mass of the Earth. The second mass is the mass of the Earth. The first mass is the mass of the satellite. All over how far they are apart squared. So it'd be 2re squared. Let me box that so you see that's one force. See how that's one force up there? So A equals F net all over the mass of what? The satellite. So boom, boom. Let's get rid of 1, 2re. So the speed that it's going to need to go is going to equal the square root of capital G, mass of the Earth, all over 2re. Hey, I can't say this enough times. Don't memorize this because it changes all the time. This is what stays the same. So always start with this. Do a little thinking and get down to there. That's the fun. All right. Let's do another one. Actually, we're out of time. We're going to do a second part to this one. So I'll see you in part 2 of circular motion.